seconds or something like that. So it's kind of awkward to look at that. Mm-hmm. Okay. So in case you wanna follow it, I paste a YouTube link in the chat, but it's I think it's quite confusing because of the delay. Okay, so it's 7 o'clock. Mark, shall I let people in?
Yep, shall I put up the first slide?
Yeah, sure.
Or we can welcome them with faces.
Okay, I hit admit all, so this will, and I see Mark has joined as well, so I'm gonna make him co-host. It doesn't matter too much, I think. It's Mark. Actually,
Albert, can I just ask, are you seeing the screen there?
I do, yes.
Is that with the full menu bar as well?
No, I don't see the menu bar anymore.
Okay, good. For some reason, it's put menu bar right across the top for me, which is handy but confusing.
Yes, yeah. People won't see any of the Zoom features you will see in your screen. So.
So welcome to everybody who's joined us so far. We're going to wait a few more minutes just for everybody to arrive. Okay, we'll make a start. So welcome everybody to session 3 of the Global Flood Partnerships sessions in November. This is the third of 4 of them. And today's session is on global flood hazard and risk modelling. So welcome everybody. Good morning, afternoon, evening, wherever you are. And hope you'll enjoy this session. We've got 4 great speakers lined up for you, and they'll be presenting on this topic. So let's see if I can get this to work. Good. Okay. So as I said, this is the third of 4. So we've already had 2 of these. You need to register separately for each session. Also, the thing to remember is that the recordings of each of the sessions are being posted on the same page that's shown in the display there. So you can go and look at individual talks, share them with your colleagues if you think they're useful. Just generally share what's going on here. So just a little bit about the GFP. Some of you may know quite a lot about us, some of you less. So just brief introduction. We're just a partnership of organizations and people that are interested in promoting better flood forecasting, monitoring and impact globally with the aim of strengthening preparedness and response and reducing global disaster losses and human life losses. So it's just a cooperative framework. So a lot of this is voluntary, and we're just a collection of people trying to kind of achieve a common goal. So please do think about joining us if your interests are similar. So one of our kind of core aims, if you like, is to bridge the gap between science and users. Because of the scale of global modelling and analysis and monitoring, it can be quite difficult to connect to the user scale. So we're particularly interested in initiatives that try and connect those different scales. So watch out for some of the talks where they're already doing that really well. The other thing we want to do is share great work that's going on. So if you've got some interesting initiatives that you're involved in and you want to share, then that's exactly the sort of thing the GFP are interested in. And we have an email service that you can share your results. And of course, you can also share and promote them in online sessions like this one. And so we'll plan to have more of these in the future. So keep your eye open for those. The other thing I want to mention is the GFP support service. So this is a kind of a relatively new initiative that's come out of lots of email requests that the GFP has had as a collective group of organizations. So we formalized it a little bit more and made this the GFP support service. It's still fairly informal in that anybody can activate it if you've got an ongoing event that you want current data for or outputs from models, then this is the ideal place to kind of get that information. And so there's plenty of information on our website about how to activate that and get current information. And the website you can find here. Here's the link for the website. I've bolded and highlighted you can join for free. This is not a paid for service. It's all free and friendly. So please do feel free to join in and see what's going on and see if it's useful to you and whether we can help you as well, share your great work. So please do join us. Okay, that's enough sales pitch. So on to how the session's going to be organized. After this introduction, there's going to be 4 speakers that have kindly agreed, and we've invited them and they've offered to talk about their work. And they're all quite different kind of projects. So they're quite interesting in their own rights. And after those presentations, we're going to have a panel discussion where we open up for questions. So the 4 speakers will be available to answer questions you have. And that can be either through audible question, and we can unmute your mic and let you share that if you raise your hand during that session. You can also just type your question straight into the chat window, and if the speaker's not presenting, of course, they may get a chance to answer that directly in the chat before the discussion session. And what I might do is, if there's some interesting questions in there, I might bring those out in the discussion session as well. So it's fairly informal, but there's a kind of presentation stage at the beginning, which we need to give the speakers chance to talk through what they've got to present to us. So that's basically how it's going to be organized. On to the speakers. So these are the speakers on the screen here. We've got speaker one is Lorenzo Alfieri from the Cima Foundation in Italy, and he's going to be talking about global modeling of seasonal mortality rates from river floods. Speaker two is Brad Peter from the University of Alabama in the US, and he's going to be talking about Google Earth Engine and implementing the flood depth estimation tool that they've been developing. And then speaker three is Rafael Chamanga. He's from the Congo Basin Water Resource Research Center, which is at the University of Kinshasa in the DRC. And he's going to be talking about the challenges of flood risk management in Africa. And then the final speaker, Antara Dasgupta from Monash University in Australia. I hope I pronounced that right. Is going to be talking about Earth observation, data assimilation, and she's also going to be looking at flood inundation forecasts. So that's an interesting crossover with the last session. So hopefully you'll see that a lot of the topics that we work with are kind of interchangeable. So that should be an interesting addition. Okay, so without further ado, I'm going to pass over to Lorenzo. So if you can get yourself ready. Oh, I forgot to introduce Albert Kettner from the Dartmouth Flood Observatory. He's my wingman today, helping me organize all the logistics. So many thanks to him. And don't blame him if anything goes wrong. That's just the way it is. Right, okay, Lorenzo, I'm going to hand over to you. I'm going to stop sharing my screen and hopefully you can share yours. Thank you.
Yes, thank you very much, Mark. I'm going to share my screen. Let me see if you can see the first slide.
Yes.
Okay, great. So today I'm going to talk about global modeling of seasonal mortality rates from river floods. It's a pleasure for me to start off this session. I'm Lorenzo Alfieri from Cima Research Foundation, and I'm also a visiting scientist at the European Commission Joint Research Center, where I've also spent the past 6 years. And also that's where most of the work I'm going to present was performed. So I want to start by thanking my GRC and also non-GRC colleagues who contributed to this work. Okay, so let's start with the motivation. In spite of the recurrent seasonal patterns, every year river floods affects millions of people and kills thousands. Although, while a considerable body of research has attempted to characterize the seasonality of global flood hazard, with some relevant examples as early as 30 years ago, there is very little research to date which has focused on the seasonality of global flood risk. We know that flood victims are unevenly distributed, and most fatalities occur in the low and middle income countries due to exposure and vulnerability levels. So knowing the timing and the magnitude of floods is key to international humanitarian assistance and for management of resources. Okay, I'm going to start with a bit of introduction on the global flood awareness system, which actually contributed with some of its data for this work. So just a brief introduction, because GLOFASS has already been mentioned a few times in the past GFP virtual meetings. GLOFASS is an operational system for early detection of river floods in the future 30 days. So it simulates forecast of ensemble stream flow prediction for the next 30 days. And these are compared with reference flood thresholds, which are obtained from a long-term discharge reanalysis. And that's exactly what I'm going to use, this discharge reanalysis version 3 that covers the years 1980 to 2018 with daily simulations. Version 3 is not yet what you can see on the website. The current one that you see is version 2.1. So this will be hopefully online next year. A little bit more information on the GLOFASS reanalysis that I've used. GLOFASS reanalysis version 3 is the latest update with a new model calibration of a global hydrological model at 0.1 degree resolution globally. We use 1,226 stations for calibration. The main advances over the previous version is in the use of ERA 5 atmospheric reanalysis for the calibration, also for the use of a slightly different model configuration, which is the full list flood model, and also of an improved calibration strategy. So you can see now, for example, in the top left graph, that the Klein-Gupta efficiency has increased. These are cumulative distribution functions. So the more the curve stays on the bottom right, and the better it is. There was a substantial improvement. And also the bias, the relative bias has improved a lot, narrowing much more towards the 0%. So now more than 60% of stations are within plus minus 20% of relative bias. Okay, so talking more about this work, we first performed sort of validation of the flood timing simulated by the GLOFAS reanalysis. So for this, we compared model simulations with about 900 stations, discharge stations, where we had at least 10 years of daily available observations. In this validation, we found quite good results in the sense that the model could predict well the observed timing of flood peaks exceeding the 98th percentile, in this case, a threshold, which corresponds more or less to 1.8 years of return period. And the median difference was 22 days for these stations, which is a conservative estimate in the sense that for the model results, we used all the 40 years of available model discharge, while for the simulations, we used only the available discharge. So this, of course, penalizes a bit stations with weak seasonality. Okay, so let's, we calculated a number of seasonal output. So starting from the day of peak, the mean day of discharge peak, sorry, including start, peak, end date, duration, frequency, and also, as you can see on the top right graph, the percent occurrence in different months of the year. So you can see how in different months there is a changing pattern of places which are more likely to experience discharge peaks. Also, the standard deviation in the top left is quite a useful indicator of flood seasonality. For example, you see with the brightest color places with a very strong seasonality. So where floods occur every year in the same days. And that is typically in the northern latitudes above 60 degrees, also on the rivers coming down from the Himalayas, and in West Africa. On the other hand, on the opposite, rivers which you see with darker colors are those with a weak seasonality, so where floods are less predictable, and that's where it's particularly important to have a flood forecasting system. Okay, so far I've spoken about flood hazard and particularly about flood intensity and frequency. Now I'm going to link this to flood risk. So first, flood magnitudes are linked to the corresponding inundation extent for different return periods. For this, we use the GRC flood inundation maps at the global scale by Francesco Dottori et al. And in this sense, it's not just a map-to-map matching, but it's really a grid-to-grid matching in the sense that each grid of the GLOFAS river network is linked to a so-called area of influence corresponding to the inundated area for different return periods. So inundated areas are then overlaid with population density maps from the global human settlement layer to estimate human exposure in all the world's countries, considering flood protection standards. So basically, expected annual exposed population is here calculated as the integral sum of the potential exposed population for frequencies between 0 and 1 divided by the flood protection levels, with the latter expressed in years of return period. Okay, I'm going to keep this one for time constraint, and we'll jump to this. We could estimate the annual population exposed to river floods, which in our estimates is 54 million people per year. You can see the spatial distribution of people exposed, which is mostly in countries in Southeast Asia, as well in some countries in Africa, typically Sudan and Nigeria. And then we move to link these estimates to estimates of flood mortality. So we used an approach proposed by Tanoue et al. In 2016, also used by Dr. et al. In 2018, where mortality rates per region and income classes, as defined by the World Bank, are inferred from two global disaster datasets, EM-DAT and Munich RE, and so linked with flood exposure according to these links. So this is quite an interesting way, in the sense that although the mortality rates are based on estimate of flood exposure, which might be biased because they are model results, then the mortality rates are sort of calibrated with the use of these two global disaster datasets. So you can see the pattern of annual mortality, which is a bit similar to the exposure, and also the relative mortality, which is, in this case, is slightly different and highlights especially countries in general in Africa, in South America, and also in parts of Asia, while you see that in other continents, like in Europe or in North America, the mortality rate is quite lower. We estimated overall 1,020 casualties from river floods globally each year. And now we move to the seasonal distribution. So we distributed this mortality according to the results from the Global analysis. And we could estimate 73% of global annual mortality from river floods between July and September, and also 75% of the total occur in Asia only. So if you look at the top right graph, you see that global mortality from river floods is dominated by summer floods in Asia, which is this big red part, peaking in August, and then followed by mortality in Africa, which has a slightly delayed peak, which is in September. And you can see countries which are more the main contributor for flood mortality, which are Pakistan, China, India, and Bangladesh. On the opposite, the 6 months between November and April contribute to only 13% of global mortality. And this is due mostly to floods in South America and Asia. And the contribution of other continents is minor due to the lower exposure and vulnerability, despite some of them, like Europe and North America, have some peaks in their mortality rates, except right in this month. Okay, so let's go to some take-home messages, which is, on average, river flooding affect 54 million people and kill 6,120 every year. And these estimates are in line with other figures reported in the literature. Summer floods in Asia are the main cause of mortality, with 63% of the total. Only 13% of global mortality is in the 6 months between November and April. And another important information is that 40% of the annual victims are just in 1 month as a country average. So of course, this is a different month depending on which country you're considering. So this is very important because we can use this information the best way and move sort of towards an annual planning of resources that should be made available for large-scale events, which need a lot of support. And for this, I want to conclude with one example. This is again related to the global flood awareness system, and particularly to a good forecast. This is about July of this year. On the basis of GLOFAS forecast, 10 days ahead of the seasonal flooding in Bangladesh, the UN released more than $5 million, making the fastest funding allocation in the UN history. So that consisted basically in distribution of cash and also with support emergency kits. And it's very interesting to see how this was done in a COVID area. So with face mask, social distancing, and proving really that pre-flood emergency support doesn't need to be done in a rush when the right information is available for use at the right time. So with this, I would like to conclude. I thank you very much. And I also want to leave you a few links, because most of the data set that were produced, all the output of this work is available for download in the GRC data catalog, as well as some other intermediate products. So thank you very much.
Thank you very much, Lorenzo. That was a great talk, very interesting, and quite a challenge in terms of scale, I think. It's good to see the connection right from the top to the bottom, or bottom to top in this case as well. So that's really cool. Thank you. Right, I realised I forgot to introduce myself actually. I'm Mark Trigg, by the way, from the University of Leeds, and I'm part of the GFP as well for quite a while now. So welcome to everybody. Right, okay, now time for our next speaker. So Brad Pitt, Peter, are you ready? I nearly called you Brad Pitt then. I'm sure you had that before. Okay. There you go.
I have heard that before. it does make it hard to Google me.
Yeah, true. Cool. Okay, over to you, Brad.
Okay, thank you. So I will be presenting today on the floodwater depth estimation tool, an implementation that we have designed for Google Earth Engine. And these are my co-authors here. I'm a geographer with the University of Alabama, working with the Surface Dynamics Modeling Lab here at UA. So I first want to acknowledge the project that this is part of, as well as some of the groups that have funded the research. So the work I'm presenting today is part of the WaterServe CyberSeed program initiative. And what this is a cyber infrastructure for analysis, visualization, and sharing of hydrological data. I have links here for your interest if you'd like to look at any of them. I'd also like to thank the Dartmouth Flood Observatory and also the Earth System Science Center at UA Huntsville, who we've partnered with as well. So some background and motivation for this project. As we know, floods are recurring natural disasters that impact the socioeconomic well-being of humans across the globe. And according to recent International Disaster Database reports, approximately 85 million people are affected globally in some way by floods each year between 2007 and 2016. And flood depth maps are critical tools for urban planning, emergency response, and the floodwater depth estimation tool is a fast geographic solution that relies on minimal inputs. And this floodwater depth estimation tool was first developed by Cohen et al. In 2018 and was later updated in 2019. So we have these fast geographic solutions, and we can make flood depth maps relatively quickly, but how can we scale the process? And if you remember the title, Google Earth Engine is one way that we are streamlining and scaling this process. So a quick overview of how the floodwater depth estimation tool works is it relies on a digital elevation model as well as a flood extent layer. So having the elevation model and the flood extent layer, you can basically identify the elevations at the boundary of the flood margins and use those elevations to create a cost surface model across the terrain and subtract that new surface from the existing elevation model to compute the difference between the two and return an estimated depth. So why Earth Engine? So one reason we decided to use Earth Engine is so that we can streamline the process by utilizing the cloud source geospatial data and analysis functionalities of Google Earth Engine. It's an open access and easy to use tool for, in this case, rapid inundation mapping. It's also a geographically scalable solution for mapping flood depths across large areas. And I'll show some examples of that in the slides. And one advantage to using Google Earth Engine that we found was that the ability to access and use DEMs stored in the Earth Engine repository greatly reduced the earlier versions of FWDAT most time-consuming processes or pre-processing. In addition, Earth Engine is an application that makes it easy to deliver and share the results more readily. So just a quick note here about the publications. The manuscript that accompanies this work is now published in IEEE Geoscience and Remote Sensing Letters if you'd like to see more about see more details about the methods. And also the code is openly available on Harvard Dataverse via this DOI. So it can be used by anyone. So here's the overall process. And in the following slide, I'll discuss a bit more simply each of the steps that FWDAT uses. But for a brief overview, first we take the DEM, as I mentioned before. And one of the novel things about the Earth Engine implementation of this model is that we've added a local outlier filtering procedure to try and correct for errors in elevation at the margins of these floods. So once we have that smooth DEM, we take those boundary pixels and use a cost surface allocation algorithm to create a new surface. So here's the step-by-step procedure, and it's a conceptual and technical replication of the floodwater depth estimation tool version 2. So it starts with DEM acquisition. There's a local outlier filtering of flood margin elevation pixels using a modified z-score. And there's an extraction of flood extent boundary pixel elevations from the DEM so that we can construct a new estimated water surface elevation using a cost accumulation algorithm. From there, we subtract the smooth DEM from the modeled flood surface elevation to calculate the depth. And then to produce a flood estimation layer that's more representative of reality, we use a low-pass convolution to smooth the layer. So here's a comparison of the results. So in the top left, or in the top left there, you can see the IRIC validation layer that we used, and this is a hydrological model that we used to compare the two FWDAT models. So here, the top center map you'll see is the floodwater depth estimation tool version 2.0. And the goal with Earth Engine was to replicate those methods so that it would work within that platform as opposed to QGIS or ArcGIS. And you can see here that we have relatively similar looking maps at the top. And you'll see as well that we achieved an RMSE that was comparable to and a little bit lower than the 2.0 version. So positive results there. And if you look at the histograms below, you can compare each of the data products. And just visually upon first glance, you can see that they are, the floodwater depth tool in Earth Engine is quite comparable to the hydrological model. And I want to point out as well that this is a 54 square kilometer area, and the export time from start to finish to run this process was only 4 minutes. So real briefly, if you're interested in using this tool, it's really easy. So To sign up for Google Earth Engine, all you need is a Gmail account to start. It's free, open access. You're usually permitted to use it instantly. From there, if you just copy the script from the Harvard Dataverse repository and paste it into your code editor, it will run immediately. The only two things that are needed are a flood extent layer and the DEM that is already in the code, and it's pulled from the Earth Engine data repository. And all of those directions are in the script itself. So once the asset is uploaded, just change the path name and follow parameterization directions and click run, and soon you'll have a map. So the parameterization options in FW.GE are, there are currently two elevation models that can be used. One is the USGS NED, which is only for the United States, and we also have available the global 30-meter SRTM elevation data. There are also options to run the outlier filtering algorithm that I mentioned. You can also add water body data to the inundation extent to get a continuous surface across your map. There's also an option to add a water body data layer uploaded by the user, or you can use the JRC global surface water data product that is already within the Earth Engine repository. And there are some other options as well for masking out water body data and areas with 0-meter flood depths. And there are also exporting options available as well. And if all you want to do is get a quick visualization of the flood depth across the surface, there is a simple visualization option as well to cut a lot of the processing steps and just get a quick map and not export. So this tool has already been used successfully in a GFP activation. One example of this is in the Midland County flooding after 2 dams failed in May of 2020. And on the left here is a flood extent layer that was produced by Robert Breckenridge at the Dartmouth Flood Observatory. So thank you for that. And on the right, you can see the floodwater depth map, basically showing the extent of the floods and also depths at each location. So to facilitate sharing these data, we also built an Earth Engine app that is publicly available and also interactable. So this website here at the bottom is live. You can visit this application, pan, zoom, query, to retrieve floodwater depths anywhere there's, at any point in the flood extent layer. So another product that was developed during this particular flood was a building impact assessment in Midland, Michigan, to show the number of buildings that were impacted and how deep the flood went at each of those in each of those areas. So you can see quite a large number of buildings were affected by floods ranging between 0 and about 1/3 of a meter. So another thing I want to point out here is the time it took to export this area. So this area was 1,182 square kilometers, and the export time for this was only 41 minutes. And these flood inundation maps were uploaded to the DFO website within 2 days of the flood event. And with the product now complete, these types of maps and products can be produced and shared in a matter of hours, depending on the availability of the flood extent data. So some of the next steps that we're working on, the next project for the floodwater depth estimation tool is to develop a standalone application on the WaterServe website to eliminate the user's need to interact with the code. Right now, it is very easy for users to extract the code and change some of the options, but we do want to make it as easy as possible to use. And another initiative that is being worked on is integration of remote sensing-based observations of flood extent packaged together with FW.GE to streamline the process even further. So some future research in this area that I'll show in a second is intersecting floodwater depth estimations with urban infrastructure to characterize damage risk. We're also looking to evaluate this model with DMs of multiple spatial resolutions, so using NED, SRTM, ALOS, and MERIT. And we're also interested to validate these models against field data on floodwater depth as availability arises. So hoping for more collaboration in that area as more floodwater depths are collected in the field. And in the future, we hope to map more floods in partnership with GFP and also the NASA Earth Science Disasters Program. So here are a couple example maps of future research that we're working on intersecting the floodwater depth with urban infrastructure. And this is the Microsoft building footprint data. On the left is across Alabama, and on the right is across Michigan. And you can see in green, each of those shapes is a building in that data set. And I've zoomed in here to an area in the bottom left where there are different depths, and there are also buildings that would be affected by these floods. And I should mention here, the flood extent layer used here is the Enviro Atlas 100-year flood layer. So it has continuous coverage across the entire conterminous US. And here I'm presenting it for just Alabama. And again, I want to note the time it took to export this extent for the entire state, which amounted to about 20,000 square kilometers of flood extent, only took 73 minutes to complete. So just some references from the presentation. And I want to thank the Global Flood Partnership. And I also have contact information here if anyone is interested to collaborate following this presentation. So thank you all for your time.
Thank you, Brad. That was very interesting. I remember seeing the first version of the tool, and it's great to see how far it's come, and it's got huge potential, and even better, it's open source as well. So yeah, really, really cool. So thank you for that talk. Okay, right, Raphael, are you ready? Yep, we can see your screen. Yep, it's gone into presentation mode. Okay, over to you, Raphael.
Yeah, thank you very much, Mark, and thank you to everyone. So I'm Raphael Chimanga from the Congo Basin Water Resource Center in DRC. And this is actually a center that was set up following some international effort on research capacity building. And Mark Trigg was very instrumental on that. So I'm now talking about the challenges of flood risk management in Africa and precisely in the Congo Basin. So I would like first to present you the Congo Basin, which is actually in Central Africa. It's actually the major river basin in Africa. As you can see, we do have several river basins in Africa, but the Congo is the major one. And so the Congo actually extends over 3.7 million square kilometers, and it generates a stream flow discharge at the outlet of about 41,000 cubic meters per second. So the main physiographic features that dominate the basin include the tropical rain forests in the basically in the central part of the basin. And we do also have large lakes and wetlands that actually dominate the hydrology of the basin. And most of the central part of the basin is actually has flat topography. So we do have also some major drainage areas in the Congo Basin. As you can see here, these are the major drainage areas. We do have Ubangi in the northern part and the Sangha also, and we do have Lualaba and Kasai in the south, and in the middle we do have let's say the central basin. And all the flow is directed to the Atlantic Ocean, where, as I said, we do have a discharge of about main discharge of about 41,000 cubic meters per second. So the main characteristics in the basin is that when it's actually dry, there is dry season. The southern part of the basin, as you can see here. So in the northern part of the basin, it's actually there is compensation of rainfall, and vice versa. So rainfall in the central part of the basin actually is there throughout. It rains in the central part of the basin throughout the year. So as you can see this from this map, you see that there is actually the distribution of rainfall over the basin, and you see that most of the rainfall, we do have abundant rainfall in the basin, in the central part of the basin, but actually vary. It varies as we depart from the central part of the basin. So there is actually the distribution, seasonal distribution of rainfall from January to December, that actually is influenced by some external factors that depend on atmospheric ocean interactions and the monsoonal process that actually act on the basin. So here I take the most downstream gauging site of the Congo Basin that is located in Kinshasa. And here you can see that we do have, this is the middle channel of the Congo Basin. And here we do have two flat peaks. The major one is in December. Actually, we are now approaching the major flat peak, and the other one is actually following. It's in April. So when you take the stream flow hydrograph, as you can see here, and you see that this is a daily stream flow hydrograph, and we match it with the percentile of flow duration curves. This is actually the 5 percentile and the 99 percentile. And we can identify some flat peaks based on this 5th percentile. And the major flood was occurred in 1963. That is actually where we reached about 80,000 cubic meters per second. But the other actually events that reached this magnitude occurred last year in 2019, but I didn't actually put this data here. So I can say that the region of the Congo River Basin covers a wide range of climatic conditions and is prone to recurrent extreme events and associated disasters, including flood, droughts, cyclones, and change in the pattern of rainfall and temperatures. So associated with this challenge are rapid population growth, uncontrolled urbanization, deforestation, and land degradation, which actually represent a serious dilemma to sustainable development in the basin. So climate change may also further exacerbate these problems with implication on agriculture, biodiversity, socioeconomic asset, and so on. So here we took data from 1964, and we analyzed this data on hydroclimate climatic disasters in the Congo Basin. So we took this data from EM-DAT. And so through analysis of this data over about 4 decades, we could see that the flood disasters are the one that are dominating in the basin. And so mostly they occur in form of riverine flood or flash floods. And you can see also that there is a trend when we start from 1964 up to the date that is shown here, 2011, we see that there is increasing trend. So, okay, we cannot say directly that this increasing trend is related to climate change, but also we can also attribute it to the fact that really there is now, much opportunities and means that allow people to collect and report data on hydroclimatic disasters. But the thing is that really the hydroclimatic disasters are increasing, but the flood disasters are also on top of all the hydroclimatic disasters. So, which means that really flood disasters are a serious problem in the Congo Basin. So, but we do have really challenges. We know that really we do have these challenges in this issue of flood disasters in the basin, but to quantify, to predict the disasters is actually a major challenge in the basin. So the first challenge, we can relate it to the monitoring network that are established in the basin and the other data. As you can see from this map, we do have the stations, monitoring stations of stream flow in the Congo Basin. So here we can take the situation before 1960s and the current situation, and you see that really there has been a serious decline in the density of stream flow gauges in the basin. And frankly speaking, this actually renders difficult the task of flood monitoring in the basin very, very difficult. So the comparison here, I just put this map of the UK in just compare to show people the real picture of what is happening. You can see the density of stream flow gauges in the UK, which has about 242,000 square kilometers, and we compare to the Congo Basin, which has about 3.7 million square kilometers. You see that really there is a problem here, and with this it would be difficult really to carry out the reliable monitoring of flood disasters in the basin. And on the right side, these are the rainfall gauges. This actually date from colonial periods. So really they have not been replaced. They are still being used. And this is also a major challenge. So the major challenge that we can identify from this presentation is that really we do have volume of data to make a good prediction. So the other challenge is about the understanding of processes in the basin. So as you can say, as you can see, the Congo Basin represents a climatic transition zone between the northern and southern Africa and eastern and western Africa. So we do have on the western Africa the Atlantic Ocean that dominates one part of the basin, and Eastern Africa we do have the Indian Ocean that also dominates. So the climatology is therefore influenced by many factors which depend on this atmospheric ocean interaction, and also monsoonal processes. So these factors include migration of the tropical rain belt, sea surface temperatures, atmospheric jets, and mesoscale convective systems. So these are actually the main drivers that modulate climate variability over the Congo Basin. So we can also say that there is poor knowledge about the interaction of these factors and how will climate change influence the seasonal distribution of rainfall in the basin. So the challenge also is associated with the poor knowledge of runoff generation mechanisms over the Congo Basin. So we do also have a problem with method of the method that could be applied for flood monitoring in the basin. So we know that rainfall runoff and the hydrodynamic models can be appropriately used to predict flood hazard and risks, but we should expect uncertainty, which is due to lack of adequate knowledge of the dynamics of hydrological processes, and also the lack of data at the required spatial and temporal scale of prediction. So, so all this really make us really to think of new approaches that could be used. And here we do have a framework that's actually of global flood prediction in the Congo Basin. There is actually a PhD student who is working on this, and below is a paper that he has actually submitted. So in this framework, we use the existing data on catchment characteristics and so on, and flood frequency analysis. So it's also based on the use of this flood model, and we input the DM, mapped DM that actually we are using, and from that we can produce the flood map, flood depths or flood extents. So we combine also with the assets that are in the basin, buildings, road, residential buildings, and some point of interest, so to estimate vulnerability. So from this, when we can overlay those flood maps produced from this flood and the assets in the basin, so we can be able to estimate exposures of structures, population, or assets. So by doing that, through this exercise, we came up with these maps of flood risks estimation based on the population that is exposed to 5 years return period, 10 years return period, 20 years return period, up to 100 years return period. So, and we have also been able to identify some hotspots for 100-year flood risk in the Congo Basin. As you can see here, there are these hotspots. For instance, here it's basically in Kinshasa that has got around 10 million of people. So the exposure is very, very high. So to conclude, I should say that the challenges of flood management are numerous at the global scale, but it varies from place to place. This variation is associated with the inherent characteristics of the physical environment, the level of socioeconomic development, and the social and political organization, which all have an influence on the level of vulnerability towards flood disasters. So in recognition of the requirements for effective floods, forecasting and disaster management system, analysis of the current status of the Congo River Basin shows that major efforts are needed with regard to processes understanding, data collection, and enabling environments. So there are some efforts that have been actually done in the basin. As you can see here, we are also implementing now some monitoring stations. For instance, in this case, it's a water level logger that is implemented in the Congo River. So we are doing some measurements. So there is really the need to combine both satellite information with in situ data. So really, I thank you for giving me this opportunity. Thank you.
Thank you, Raphael. That was very interesting. And it's quite amazing to see some of the challenges that you have in terms of defining and managing flood risk, particularly in such a vast basin. If I remember right, it's about 3.7 million square kilometers, so a whole different scale to what we have in the UK. And the data challenges seem quite acute as well. So there seem to be a few questions about that in the chat you might want to have a look at. Okay, thank you. And the other thing might be worth mentioning is I think you're using one of the models that's used for global flood mapping as well, the list flood Fathom model that's been published before. So this is actually an application of a global model at a albeit a very large catchment, but at a catchment scale. So it's really cool. Okay, so on to our final speaker, Antara. Hopefully you're about ready. If I don't know whether Raphael needs to stop sharing first. Yeah, Raphael, could you stop sharing your screen? And here we go. Perfect.
I could override it. Sorry, Raphael.
Brilliant. Okay, so I'll hand over to you now.
Thanks,
Thank you.
Mark. I'm gonna just minimize this and let's go. Hi, everyone. And today I'm going to be talking about mainly my journey through the PhD of answering one very important question that I guess all of us have often wondered about, which is how can we best leverage the massive amounts of Earth observation data that we are producing for improved flood inundation forecasts? And the main question that I was chasing after was, what if most satellite-based flood observations could significantly improve forecasts? So what if my before forecast could look like this and have a lot of false alarms and problems, and my after forecast, after integrating maybe just one remote satellite observation, could look somewhat like this, where I've reduced most of the false alarms? Well, how will it work? One of the ways to do it is to try and make improvements at every step of the process. So we try to first improve the flood extents that we can derive from our satellites. We then try to improve the integration algorithm of these flood extents with our models that we were hearing about so far. And finally, what I wanted to look at was, what are the best ways, or which are the best images that we could acquire to facilitate this process as best as possible? So in the interest of brevity, I will be omitting the calibration part and focusing on this part today. Let's dive in. And the first part of this project was to improve the radar-based flood mapping. And the main challenges in front of us were major histogram dependence and over-reliance on deterministic outcomes. So let's first talk about the first problem here. So a typical flooded image histogram is assumed to look somewhat like this, where we have a nice water pixel distribution and a nice land pixel distribution, a nice bimodal histogram, and then we can divide it using a binary threshold and get a flood map. In reality, however, there's often significant amounts of overlap, which prohibits this sort of threshold-based mapping, or at least introduces significant amounts of uncertainty. What we can do then is try and use a probabilistic distribution. The most commonly used one is the Gaussian mixture model, of course, as these curves can be assumed to be Gaussian, and we can then parameterize these distributions in a data-driven manner. And this still, it kind of helps us with the deterministic threshold problem, but it does not help us with the histogram dependence. So what we proposed to do for that was image texture optimization. And the reason for doing this is essentially that in a histogram, which is evenly divided between flood and non-flood pixels, there could still be a whole variety of different patterns that could exist in the actual flood extent. And we essentially could miss them if we only rely on the intensity values. So trying to incorporate texture led to a different set of problems, which was how to objectively select them or how to retain only the information that we need, because we cannot indefinitely increase processing time. So we tried to come up with an objective methodology to achieve this. We first calculated the sensible variance within each of the classes, so the flood and non-flood classes, and based on the data resolution, which in our case was Cosmos SkyMet data at 3 meters. So we got a lag distance of 3 pixels. Then we removed the effect of directionality from texture. So as you could imagine that if we are checking, if we want to create a texture map of, say, this central square, depending on which angle I'm looking at, the pattern that I would discover would be different. So in order to remove that effect, we averaged out the textures in all directions. And then, as I said, we cannot indefinitely increase processing time. So we condensed all our information into the minimum possible number of bands using a dimensionality reduction technique. And we had our optimized texture features. I'm showing here the results of a fuzzy comparison between SAR-based flood maps and aerial photo-based probabilistic flood maps. And the comparisons on the screen are for a neurofuzzy classifier implemented to the SAR intensity image alone, a SAR image enhanced with the standard textures used in literature. And the final panel shows the classification enhanced using our optimized textures. The blue colors are a perfect match, the red colors are a perfect mismatch. And it quickly becomes evident that as we go from the left panel to the right panel, we are significantly able to reduce uncertainty. And one more interesting finding is that when we add some texture, so any texture, we do not make as much improvements as we would with optimized texture. Now, looking at a lump statistic, which can quantify what we see here, we look at a reliability diagram and we try to calculate the weighted RMSC from this reliability diagram. So what we are looking at is the plot between the observed proportion of wet pixels in the validation data and the fuzzy membership value observed in the SAR map. And the 1-1 line indicates perfect agreement. And the triangles, which are the SAR plus optimized texture, we can see are already the closest to the 1-1 line. And in terms of the weighted RMSC statistic, we make about a 54% improvement. But what's even more vital to note is that the addition of some texture only makes very negligible improvements, while when we optimize our texture information, we are able to reduce our errors significantly. So we now had a working flood extent mapping algorithm. It was working as well as we could hope. So we needed a new method to combine these satellite-based flood maps with our models. And here, the main challenge was having the sensitivity of our metric that we use to compare our models to the observation. So essentially how probabilistic forecasts work, and please forgive me, those of you who are already familiar with it, we have an ensemble of models which we expect or hope that will capture the uncertainty in any one of them, in any one of those models. And at any time during the flood event, we hope that at least one of them or a combination of these models is true. And the problem is when we want to choose that metric for flood extents, the difference between models is usually very limited to be able to capture it with these metrics, since the common area often or mostly outweighs the area that is different between different models. And the solution we propose to this is to embed a likelihood, which I'm going to come to in a minute, within a particle filter algorithm. Particle filters do exactly this. So we have our ensemble of models and we have no information about which one is right. So we assume that all of them are equally likely to be true. And as and when we get observations, we iteratively update our model ensemble probabilities or the likelihood of any of them being true, such that we can eventually estimate the true state PDF. Sorry, the final ranking of models which give us the best forecast. So here we propose to use mutual information as the likelihood which allows this model ranking. And mutual information essentially starts with the assumption that the model ensemble and the observation are completely independent. And if they are statistically independent, the joint distribution of these two should be equal to, in theory, to the product of the marginals. Getting a little bit technical here, but I'm going to try to walk us through it without getting too boring. So basically what we want to do is we want to get the distance between this joint distribution and the product of the marginals, which would then quantify the shared information between both of these. And this blue shaded distance that you can see from these two example probabilistic distributions are essentially what we are after. And as I said, sensitivity was was one of the key issues that we were trying to address. So we introduced a rescaling factor to sort of zoom into this metric and be able to see the differences between our models. This worked fairly well in our test catchment, which was Clarence in New South Wales, Australia. And my test event was the 2011 flood event, for which you can see the hydrograph on screen. We had 2 Cosmos SkyMet images and the open loop ensemble, which is the ensemble without any assimilation or integration with remote sensing data, is shown here. And the mean is also shown here, along with the truth, which was used as the base scenario, or the observed flows, which were used as the base scenario to generate this ensemble. And we found that our assimilation algorithm works fairly well, actually. Within the channel here, we are looking at this point, Grafton, which is one of the key areas to get right, since there are a lot of settlements here, which are at risk from the flooding. And the green line shows the true stage, while the black line shows the open loop, again, without any assimilation. And the dashed magenta line shows the assimilated vector. Image positions are shown in dashed black lines, and we can see that following both the assimilation time steps, we actually drag our open loop vector, the state vector, quite close to our truth. So the water levels actually follow the truth very closely after the assimilation for a long time after the assimilation. We also saw that not just in the channel, but even in the floodplain, in terms of flood extent, we were able to improve the critical success index, which measures the ratio of the hits to the hits, misses, and false alarms, by about more than 10% for at least 3 days. So with these encouraging results, we now wanted to find the best observations that could result in the maximum improvements for our flood forecasts. And the main reason for trying to evaluate this was that for large catchments, often we can observe only small parts of the catchment. And since we can task satellite acquisition, it makes sense to then evaluate which part of the catchment we should ideally be looking at. And the potential solution to this was visualized as sort of designing targeted observation strategies based on river reach characteristics. And the way we went about it in our catchment was using a combination of the channel geometry and the floodplain morphology. And based on this, we identified 3 distinct subreaches in our catchment. The first one with limited backwater effects and actually no backwater effects and a narrow and steep valley, mostly linear flows. The second one with strong meandering, strongly dynamic flows, but a flat, gentle valley and very limited backwater effects. And finally, we had subreach 3, which was quite hydrodynamic, but also affected by dominant backwater effects from the very high tides at Yamba. So trying to visualize our thought here. So how does the ensemble look in terms of extent? So this is the image we were looking at in the couple of slides ago. And at this example observation time, I've sort of extracted the flood extents for this high discharge particle and this low discharge particle. And we can see here that they significantly differ, A. And B, when we compare them to the flood probability map, they should ideally have very different weights. And C, that when we look at the extent variability within the extents of all the particles, here particles means the model ensembles that we were previously referring to, we see that there's mainly the variation is limited to this part, at least at this time step. So with this sort of visual in mind, let's approach our results. Here we will be looking at the Breyer skill scores, which measure the improvement in the quadratic errors in the open loop forecast against the assimilated forecast. And this is just a snapshot of the catchment to remind us all where the gauges are. And in each of the columns, the gauges are, only those gauges are listed which are within that particular subreach. And what we're looking at here is essentially the Brier scale score plots with respect to the satellite acquisition time. So each point represents the improvement in the assimilated forecast versus the open loop forecast, and can be interpreted as percentages. So you could say this point is about 80% better than the open loop. And what we mainly want to be looking at is which image or which of these single images leads to the maximum improvements in our forecast. And a Brier scale score of 1 means 100% improvement. So the first really encouraging thing is that a lot of images that we use across the hydrograph produce quite notable improvements. But let's look at also a bit of the discouraging news. So we do degrade our forecasts in places. So let's try to diagnose when and where that happens. And the first thing that becomes quite obvious is that when we assimilate downstream, so when we are assimilating images only in subreach 3, that is the blue curve, we find that the impact is not so great in subreaches 2 and especially subreach 1. And it looks like we're unable to select the models which perform well based on subreach 3, we're unable to select models which perform well in subreach 1 based on subreach 3, which is expected, of course, since we cannot propagate our improvements upstream as such. But when we look at subreach 1, also the red curve here, we can see that even when we propagate our improvements downstream, the improvements from subreach 1 seem quite inconsistent. This is maybe relevant to what we saw in the previous slide, where the variability in extents actually changes across each of these subreaches as we traverse the flood event. And the most stable we realized was assimilating in subreach 2, which was sort of still dynamic. So a bit of extent variability with flat floodplains, but not as much dominant backwater effects, which would then make the dominant source of error something else. Whereas here we were looking at mainly inflow errors. And we found that assimilating in subreach 2 does not actually degrade the forecast downstream at all. And we actually get fairly good improvements, or at least greater than 30% improvements in all the cases that we expected to work. So the key thing to note from this experiment was that based on where we are in the event and how the catchment is, it might be possible to design a good observation strategy, which would lead to then the maximum possible improvement from our assimilation. The way forward then is to develop a better observation localization strategy in space and in time, which would help us then to scale to larger areas. We want to test our approach for different catchments and more real cases to evaluate all sorts of possible cases where maybe it implodes. And finally, our goal is to scale for global implementation and try and integrate this approach with GLOFAS. And thank you so much for your time and for having me here. I'm happy to take any questions or feedback now.
Thank you, Antara. So that was a great example of the cutting edge science that's going into these methods and tools. So much appreciated for sharing that with us. Okay, so now we're going to the open questions session. I noticed there's been a few questions already in the chat window. Antara, you probably need to catch up with those, but have a look and see what's in there. But I noticed some of them have already been answered. So if Brad, Raphael and Tara, you can join me for questions, as well as Lorenzo. I think you're still in somewhere. I can't see on my screen, but I'm sure you're there. Oh, there you are. Zoom hiding you in the corner now. Okay, so please put any questions you have, or raise your hands so that I can see you looking to ask a question, and I'll unmute you. And Albert can help me with this, hopefully, in terms of unmuting and letting people ask questions. Cool. Okay. So I picked up a few questions that came across in the chat window that might be worth exploring as people think of questions to put. Raphael, I noticed there were a couple of questions about the decline in monitoring. So I wondered if you wanted to kind of address that question verbally, but also perhaps look forward to whether global data sets have a value to the catchment in terms of flood management, and if that's something that is going to help with that data gap.
Yeah, thank you very much. I've already been addressing some of the questions in the chat. So the first, I would say that the government that took the power just after the independence didn't have water management or water resource monitoring as the priority. So this actually contributed to the decline in the monitoring stations. But as you can see also, the basin is very large, and so there are very remote areas. Maintaining hydrometric stations in these basins, in these remote areas, is not really easy. It requires expertise, it requires funds, it requires also a lot of technical resources, which actually are very challenging for these developing countries. So the idea also here, I've got another question about, so should we go for remote sensing data or in situ stations? So I think there is need to combine both. As we are using, now we are going to be using more and more the satellite data, but we find that there's still need to validate this data based on the in situ observed data. So given the signal that is not being really captured over the Congo Basin, so there is really the option could be that we select some location to implement the monitoring stations that could be used to validate the satellite data. So the value, there is really value. There are a lot of global data set now, but still we do have that challenge of validating those data, those global data on for use at local scale. There is this heterogeneity and this variability of climate, for instance, climate variables, climate system in the basin. So capturing this climate signal at local scale is very, very important, because so when we talk about management, about prediction, we don't only see the wider basin, but we also see the local scale of management where prediction is needed. So, and this is actually where we still have challenge from using the global data to validate them at the local scale. So if we can be able to implement some stations at selected sites and use those stations to validate the many global data sets that are now available, that will be of much benefit for the Congo Basin.
Thank you, Raphael. That was a really interesting answer. I think if anybody wants to collaborate with Raphael, I think he'd be more than interested to sort of utilize global data sets at the Congo scale, because he's already doing that. So yeah, do reach out to him if you want to collaborate on science in the Congo particularly. Brad, there was quite a lot of interest in the open access kind of questions to do with the model that you're developing. I was wondering, just for my own curiosity really, what was the driver behind making it open access? Was it to developer community to increase development of the tool, or is it more to do with ease of access and giving people options of using the tool?
Mostly to do with ease of access and make it available to as many people as possible, and also to facilitate collaboration. And in general, one of my philosophies is to produce open access science, because I'm the beneficiary of that type of science as well. And when I can access other people's code and replicate it, it ultimately ends up with better science being done. So I want to contribute to that trend as often as I can.
That's great. That's good. On the question of scale, Lorenzo, I noticed you were talking on the last slide about actually the active use of the GLOFASS model for forecasting. At what sort of scale does that applicability apply, do you think? Because obviously it's a global model, but it can be used at basin scale. At what scale do you have to be careful about the application of your model?
Okay, well, certainly GLOFASS was designed for medium to large scale river basins. So for example, in the case I showed before, it was in the Ganges-Brahmaputra river basin, where the GLOFASS forecast predicted a peak in the flows in Bangladesh around 10 days before. So of course, this is a result of the anticipation given by a good meteorological forecast and by the delay given by the routing through the large rivers. Then of course, as we go to, we had also examples with 15 or 20 days of good forecast on the discharge peak. What we have to be more careful is surely on a small, very small scale basin, because there are a number of limitations given by the resolution, time, space resolution of the modeling simulation. And then, of course, in catchments which are not calibrated, then we also have to be more careful. In the case that I showed, the support from the UN was not given straight away after the GLOFASS forecast, but there was like a first raising of awareness, and that was then followed closely by the local agency. And I think it was the National Hydrological Center that monitored, and also with the help of their prediction. Basically, it was an overall evaluation, and at some point they decided, okay, now it's time to trigger the support.
I can see Albert's raised his hand physically.
Yeah,
Go on, Albert, jump in.
This is because I cannot raise, since I'm the host, I cannot raise my own hand, I think, in the, but anyway, I got actually a follow-up question for Brad. I remember the earlier versions of the depth tool had some difficulty, I think, when you have those detailed flood maps. You have many polygons or pixels that are showing flood, but they're not all connected, right? So there could be thousands little flooded areas. And I remember that was, I think, computational challenging to calculate the depth for each of those small ponds or small areas that were, filled with water. Has the Google Earth Engine tool improved in that way, that it will, maybe ignore the small areas, or that it, has no problem with calculating so many small standing bodies of water?
Yeah, computationally with Earth Engine, it's no problem. With the Michigan, it depends a little bit on the spatial resolution of the data, but with the Midland County example, that had a lot of small water bodies detected, just strewn across the landscape. And that one only took 41 minutes to run. So even at that scale, it's quite computationally efficient. In general, the better results emerge from a continuous surface to get a better picture of the overall flood. But yeah, computationally, it's a big advantage over other systems.
Cool. Thank you.
Sure, thanks.
I've got a question for Antara about scale as well, but this time the other way. How are you going to scale? You finished your last slide on, you want to go to a global scale. What do you think are the main challenges to taking something, which is quite experimental and quite complex as well to that sort of scale?
Excellent question, one that keeps me up at night. And I think the main challenge, I wish it was the complicatedness of the issue to implement, but the main challenge is just running a hydraulic model at that scale, at a global scale, and have it run in real time. That is unfortunately still the main problem that we're looking at. But if I could for a moment close my eyes to that problem, what we need to do for scale is first sort of design a spatial. I'm going to little bit technical on the response here. We need to basically design a decay algorithm which allows us to relax the influence of the observation both in space and in time, because I guess it gets the forecast gets independent quite quickly of the actual observation. And what I also think is required is that first step that we did of the targeted observation design. We maybe need to look at the DEMs across the world, maybe a Google Earth Engine based tool to do that, where we could sort of build a lookup table so that we can just, when we want to, so okay, we have a flood in Congo, for instance, we can just trigger the most, the best places to acquire images, and then the satellite can acquire images exactly, at the places that it can hit while it's doing its daily overpass. So this is the kind of very idealized picture we have in our head. But we're also, we've applied, as I said, for in the chat for some funding to try and implement this to GLOFAST forecasts. And we want to look at if we can improve somehow the 30-day forecast and add capabilities of flood inundation extent and depth to that in a forecasting scenario. I think that would be quite revolutionary for flood management.
Yeah, very interesting. I think we'll keep you busy for a future career, I think. One other question, just out of interest, what was the motivation behind doing your particular project? What was the driver behind that? Maybe a personal question, I don't know.
Yeah, slightly, but I'm going to answer because it was very interesting. So I was, I think most of us here would have heard about the absolutely devastating Uttarakhand floods of 2013. And at the time I was living in Uttarakhand and we were cut off from civilizations. We used to live very close to the river and they were like, not nice images. Okay, so there were bodies and stuff floating down the river. It was just all kinds of really bad stuff happening. And when I sort of dove in deeper to my master's, I found out that this was mainly happening due to poor emergency management problems. And we had some infrastructure in place, but there was no sort of trigger happening. And so slowly my belief in sort of global systems was increased, where I thought that, okay, if we have sort of a unified global system, well, then everybody can access it. And then we will hopefully have lesser excuses to let something of that scale unfold.
Thank you. That's a nice reminder of the reality on the ground of floods, that they often come with huge personal cost. And I think probably a lot of people here are kind of motivated by that. So it's nice a reminder, I guess. The one question we've had in the chat window recently was from Robert Goldhammer. And the question relates to using the X year return period flood terminology. So this is a bit of a can of worms that I think comes up fairly regular basis for discussion, but doesn't seem to go away, which I think is Robert's point. So he's asking, you know, how does everybody feel about stop using that terminology and move to something else? Anybody want to open up with an answer to that one?
That's a very good. Oh, go ahead, Brett.
I was just going to admit that I'm guilty of having that misunderstanding. So any improvement in clarity is something that I would approve. Those are my thoughts about that.
Albert, you were going to say something?
Yeah, I'm on the same page. It is confusing if you're not familiar with the concept, I think. So if people not working on a day-to-day basis with flooding and how to express certain floods, but you're suddenly affected by it, and you read, okay, this is a 100-year flood, and 5 years later your town is again hit with a 100-year flood, and you're wondering, why is this happening, right? But I don't know the alternative. That's kind of, and I think that's where the flooding community is kind of, so far I have not seen a good alternative, I guess. That's the problem. I think the USGS here slowly moved away from those expressions of, you know, the one in a 100-year flood, but yeah. Yeah,
I was going to say, certainly in the UK, we officially use annual exceedance probability, which is the inverse of the return period, but it doesn't get a big take up because people find understanding probabilities harder than a number of years. But unfortunately, that's still a probability. It's just they don't realize it, I guess. So I have the same challenge. In fact, only yesterday I was teaching the undergrads literally about return periods and annual exceedance probability and the challenges with the wording. So yeah, I think it's not something that's going away quick. So if anybody's got a great solution, do let us know. Okay, just seeing if there's any other questions.
Yeah, and I just want to point out that if people have a question and are and the question is such that it's hard to type on the chat, just raise your hand, and you can do that by clicking on the menu bar on the participants, and then there is a raised hand feature, so we can open your mic and you can ask your question. So.
I had a small question for Brad. Could I go?
Yeah, go for it.
Okay. Thanks so much for for writing the tool, which is quite awesome and easy to use, it looks like, and for your presentation. I just wanted to know, you showed your validation for a very small area. How do you think the validation results will scale when you look at the sort of catchments you were showing later? So maybe in Michigan, etc. If you want to maybe take a guess at how it would look.
Well, I have some anecdotal evidence right now from the NASA, I don't want to get the name wrong, NASA Earth Science System Center, evaluating some floods where they have other validation data, and they've said that the model is performing quite well. One of the challenges that we are running into with validation is that there's just an overall absence of floodwater depth data to validate these models against. So we're relying on the hydraulic models to do that. But yeah, so there are other groups as well who are using it right now. Someone from Deltares gave it a spin, and the feedback we got from them was positive as well. So we're hoping to do more of those types of collaborations with others who have data that we can validate these models against. So hopefully someone out there is hearing that and wants to collaborate. Thank you.
Thank you.
That's cool. I've got a question for Raphael. Something that's kind of been at the back of my mind for quite a while and comes up in the Global Flood Partnership discussions quite a bit, which is related to the fact that we're developing all these global models, which obviously are global by definition, but they often, because of the nature of the way they're built, they're large models or need quite a lot of resources to build, and tends to be a bit top down. And we're always concerned that the danger is that we're not actually building the right tools for the questions. So the question I put to you is related to that, really. Is there a danger that all these great models and things are undermining local institutions that are essentially trying to collect data, like the gauging station data that you mentioned in your talk? Will the local institutions say, well, we don't need to collect data, we'll just use this model or something like that? Is that a real danger, do you see, in the DRC?
Thank you very much, Mark, for this excellent question. So really, it's not only about this global model, but it's also about this satellite data that have been really produced but not been used. So really, we say for now there's nothing. There are no monitoring stations, but there are this global data. So the question would be, how can you use this global data just to give some sense of management, to guide management in the basin? So this is the first impression I have, that really it could be used to guide the first choice management. But in reality, really we need, because when you are talking about management, when you are talking about prediction, so it's not really about large scale, but it's about the scale of management. The scale of management, we have got cities, we have got agriculture areas, we have got navigation channels and so on. These are the scales of our management. So how can we get our models, our products validated at this scale of management? And this is where I wanted also to come up with a question to Lorenzo, because I saw from his presentation there was this on-off scale, and you can see that the whole Congo Basin with about 9 countries and so on. So it's actually the scale is 1, and you find out that the prediction leads to one result. But in reality, when we come to the ground, we still find that there are a lot of discrepancies, there are a lot of variabilities, which need really to be taken into consideration for prediction. So to conclude, to directly respond to your question is that, okay, these global models are being used. They don't directly give answers to the issues in the ground, but they can still guide first management choices.
Okay, thank you. That's useful. Do you have any advice for people trying to build global models on how to engage with that management level? Because that seems to me to be a big challenge, because if you're building something globally, you can't obviously engage with every single person on the planet. So there needs to be some way of kind of engaging with that management system. So the simple question is, how would a global modeling person engage with the management issues in the DRC, for example? Sorry, that was for you, Raphael.
That was for me.
Yeah.
Okay.
Just to follow on.
Please can
so repeat the question. Is what I was asking is just a little follow-on question. Is okay. So it could the answer you gave was that they could be useful for management, obviously with certain limitations. But how do global modelers or remote sensing developers engage with that management level so that they make sure their tools are appropriate for that question on the ground? You know, using the DRC as an example, for example.
Yeah, really, this is where we need dialogue between, you know, model developers and you know, users. So we need to engage in this dialogue, because when people are using building models and so on, this should be used at local scale. But then, so if we don't get information from local scale on the validation of these models, so really this global model are going to be useless. So really, it's a difficult question. It's not easy one, but to me, I think that really we need to engage in dialogues. There are now, you know, people, you know, going into that area of developing global models, developing product at global scales and so on. But you still find that really there is little use of this global data at local scale. Let's take, for instance, the case of satellite altimetry data. We do have thousands of data generated from satellite altimetry. So the idea was to use this data to start, you know, monitoring water level, for instance, for navigation, to start, you know, converting water level into discharge and so on. But so far, it has not been done. So we are still, while waiting for this data to be used, and you know, not putting much effort into the implementation of a station at local scale. So there is still gap that is actually into knowledge development, knowledge generation, but also gap in management to address some issues of day-to-day lives. So really, this is why I say we need to engage into dialogue between scientists, between users, professionals. We need really to have a kind of dialogue, and a framework like this one really could generate a recommendation that could lead to that sort of dialogue.
Excellent, thank you. Lorenzo, I wondered if you wanted to come in there and maybe put your thoughts, because you've been involved in global scale models for a while now and have seen various aspects of that. I wonder what your kind of thoughts and experience are on that question.
Yes, definitely, Mark. I think in this regard is, well, first of all, GLOFAS is, in its name, is about flood awareness. So in the sense that we know that we don't aim to forecast the exact water level in a certain day or specific discharge, but we want to give awareness that in a week or in 2 weeks, there can be a potentially severe event. So I see this as a sort of multi-layered, multi-level change, where each of us, and I mean us because I'm here referring to the Global Flood Partnership, as a role to to use their product and identify where each product is useful at best. And so try to build up this chain, which is most efficient, like we have tried to describe already in the past. For example, giving a first awareness, let's say 1 week ahead, and then passing it to like a local center that is better able to forecast water levels because it has some specific calibration. And this then goes further, of course, to the users of this data and to the emergency responders. So I think this is an important role that the GFP can and should promote, so that everybody can give their little contribution, but overall that's maybe the best. It's about taking out the best that we can achieve now.
Excellent answer. That's a good one. Okay, I don't see any other questions. Have I missed any in the chat, Albert? Albert, please do jump in.
Not sure if you missed any in the chat, but I do have a general question on on forecasting and modeling of floods. So the talks that we have seen here, I mean, they were excellent, but they are mainly focused on river flooding. And, you know, some of the other types of flooding, flash flooding, storm surges, cause actually many lives, many fatalities as well. Is anybody aware? I know that in a NASA Geo supported effort, Andrew from the Red Cross Climate Center is focusing more on flash floods, but is anybody aware of other initiatives that do kind of develop global models that try to forecast flash floods or storm surges for that matter? I think for storm surges there is actually an effort, but I don't think those groups are really connected to the Global Flood Partnership. But I was more wondering in flash floods if there are any global efforts on that side. Okay, and I see a comment from Lucy that there are forecast models for surface water. And that would be surface water in general, so it doesn't really matter if it is what is it, a storm surge or river flood. There is no differentiation for that. Lucy, do I understand that correct or not? I see actually many people are responding to this, so that's good. If somebody wants to speak out, feel free to raise your hand and we can open the mic. I have a hard time keeping track of the chat.
Yeah, I've seen some of the data-scarce work presented previously, which is starting to integrate river and coastal, which is good. And I think, if I'm correct, the Fathom global flood model also looks at pluvial scale risk, not necessarily flash flooding per se, but pluvial flooding definitely. So I think it's beginning. Yeah, and coastal now. Okay. Mm-hmm. Is that where did they get the coastal boundaries from? Is that the data-scarce model probably?
No idea.
Okay.
The Del 3D. Yeah, they have Del 3D, and then they X Beach, I think, is part of their.
So it sounds like it's coming, but yeah, it's river flooding has been a topic for quite a while now, so it's good to see it expanding. Okay, yeah, JBA have a model that's used in the UK actually for the UK national level flood risk assessment. So I wouldn't be surprised if that's applied globally as well now. Although obviously the data going into it's different.
Okay, this is all good. Yeah, I can save the chat and post that afterwards or something, because they're all good suggestions in here, and maybe some people want to reach out to those groups. I certainly would.
Somebody's asked about dam burst models as well, presumably at a global scale, and I think that's something that's being looked at. I think Fathom are trying to do something like that, but I think it's early days. Possibly you'd have to pass that question to them directly, but I know there is some interest in that for sure. I know I'm interested in it. Okay. So I'm just thinking with the time now, it's probably a good time to start wrapping up. So if anybody's got any questions, last questions, you've got a few minutes to post them now. But I just want to thank all of the speakers for their time and their efforts in presenting their great work for everybody to see. It's much appreciated. And thank you for supporting the Global Flood Partnership by attending, everybody. It's great to see so many people at these events, and it keeps us going on a voluntary basis to see so many people interested. And do let us know if there's anything we can do to improve what we're doing. We're open to suggestions, and we would love to see you kind of join the partnership and engage with what we're doing. So please, please do. Join us all, and thank you, everybody. No questions, no remaining questions. Good. Okay. Thank you, everybody, and much appreciated. And see you at the next week's one. Bye.
Thank you, Mark.
Thank you.
See you all.
Thank you all.
Bye.
Thanks, Mark.
Thank you.
Thanks, Albert. Bye.
Yeah.
Bye-bye.
Thank you.
Thank you.
All right, and I'm going to close it for everybody. So thanks. The recordings will be here in 1 or 2 days or something on the JRC
Thanks, Albert.
website.
Much appreciated.
Thank you. See you, Mark.
Bye.
See you all.
See you all.
See you, Lorenzo.
Thanks.